Hello everyone, welcome back to the session. I hope I'm clearly audible to all of you. Guys, am I audible to all of you? Hi, can someone please confirm if okay, audible. Perfect. Cool. So let's get started. In the session yesterday, we spoke about something very amazing, which was understanding the inter-VLAN routing with the help of router on a stick mechanism. And then we also spoke about HSRP, which basically helps us in implementing first hop redundancy gateway protocol. I'm sharing my screen, and today we are going to speak about another amazing technology called spanning tree protocol. So I'll just quickly share my screen and then we are good to get started. Sure, guys, here is the notes of yesterday's session, first hop redundancy protocol. Let me put it in the Telegram group for you all. And today, like I said, we are going to look at spanning tree protocol. So let's understand what is spanning tree protocol and where exactly it is beneficial or where exactly it's gonna help us in layer 2 scenarios. When we speak about spanning tree protocol, it's used for avoiding the loops in a layer 2 scenario. Now, where do we find loops? That's the very first question, right? So when we talk about a normal topology of two switches connected together, let's say like this. This is my switch 1. This is my switch 2. It's a layer 2 topology, right? We have just two layer 2 devices connecting to each other. So this particular topology is a layer 2 topology. If I add another switch here, let's say switch 3, and connect my switch 1 to switch 3 like this, then basically I have provided connectivity between all three switches. But if switch 1 wants to communicate to switch 3, it has only one way. If switch 1 wants to communicate to switch 2, it has only one way. Similarly, switch 2 can only communicate to switch 1 via only one possible way, which is not a very good topology design. So when we speak about designing a network, we make sure that there is link redundancy. Okay. And what is link redundancy? It is basically the method through which an alternative path can be used if the primary path goes down. For example, if this link goes down, I don't have any way of switch 2 to make a communication with switch 1 or switch 3, right? Similarly, if switch 1 to switch three's connectivity goes down, there is no alternative way through which switch 1 can reach to switch 3 or switch 2, correct? So we implement redundancy by adding a redundant path like this. Now this is a redundant topology. Clear, guys? But along with redundancy, it also brings a problem. It brings a problem of layer 2 loops. What are layer 2 loops? Let's understand. In this situation, if let's say switch 1 is connected to a PC and this PC generates a ARP request. First of all, let me know, do you agree that it will be broadcasted? A ARP request is broadcasted, right? Perfect. So it will be sent to switch 2 as well as to switch 3, correct? Because it's a broadcast message. When switch 2 will receive it, switch 2 will also forward it here. And when switch 3 will receive it here, it will also forward it here. So basically my packet travels like this from both the sides. Switch 3 will also keep on making it revolve around these devices. This is called a layer 2 loop. And this loop never stops. Why? Because on layer 2, we don't have the concept of TTL. What is TTL? TTL stands for time to live. Time to live is a value which keeps on decrementing whenever a packet crosses any hop. So basically, if I speak about a layer 3 topology, let's say it is router number 1 here, router number 2 here, router number 3 here, router number 4 here. Okay. There is a packet which R1 has generated with a TTL of, let's say 10. So when this packet will be received by router 2, here my TTL will get decremented by 1. Okay. Similarly, when this packet will be received by R3, which is my next hop, my TTL value will be decremented by 1. So when TTL becomes 0, the packet becomes dead. Okay. But in layer 2, we don't have any TTL concept. I mean, it doesn't works on layer 2. It is a layer 3 capability. So that means my packet will never die. It will keep on revolving between these devices. Make sense? So to avoid this layer 2 loop, what we have is we have a concept, a very amazing concept called spanning tree protocol. Spanning tree protocol is a concept or a technology or a protocol which is going to be enabled on the devices by default. You need not to enable it manually by making some configurations. Okay, it works by default. So the moment you will connect 3 devices in a redundant topology like this, it will enable spanning tree protocol and will basically make sure that loops do not happen or loop doesn't happen in this redundant topology. The question is, how will it make sure that loops doesn't happen? It will make sure that there is no loops in this redundant topology by blocking one interface. Okay. But by blocking, am I not removing the redundancy concept? Isn't it? Like if I blocked this interface, then that means switch 2 has only one way of reaching switch 1. The alternative path is gone now. But guys, there is the trick here, or we can say here is the good part of spanning tree. The moment any of the primary link goes down, let's say this link goes down, so this blocked interface will change into an forwarding interface, and this link of mine will become an active link. So it automatically enables the blocked interface that the moment there is a link failure in the topology. Make sense? That's basically the role of spanning tree protocol. Are we clear what exactly spanning tree protocol does? That's perfect. Now, the question is that how will I decide that which interface am I supposed to block? Which interface am I supposed to keep in the forwarding mode? Which interface will be used for forwarding data? Which is going to be blocked like? So that happens with the help of elections. Okay. So let's understand how spanning tree protocol works. It works with the help of three elections. First is electing the root bridge. Second is electing the root port. And third is electing the designated port. First of all, we need to understand how the first election happens and what is exactly a root bridge. So let's get into the details of election of root bridge. Now we also have a question that how exactly do they know if the interface is up or down, and how do they monitor? So what they do is they exchange a packet every 2 seconds called BPDU. BPDU stands for Bridge Protocol Data Unit. Okay, guys, you must be wondering what is this bridge? Yeah, root bridge, then bridge protocol data unit. So before switches, there used to be devices called bridges, and spanning tree protocol is a legacy protocol, has been using for years now. And the terminology is set as bridge only. So whenever I say bridge, it simply means that we are talking about switches only. Okay. So basically, they exchange these BPDU messages, Bridge Protocol Data Unit messages, every 2 seconds. Clear? Inside the BPDU message, we find bridge ID. And a bridge ID is made up of two things: priority value plus MAC address. The size of priority value is 2 bytes. What is the size of MAC address? Let me know. 48 bits, or we can say 6 bytes, correct? So what will be the size of bridge ID? My bridge ID is going to be of 8 bytes. So the first election which we have happens on the basis of lowest bridge ID, in which first we consider lowest priority value. And if the priority is same, then we consider lowest MAC address. So between the three switches, I will first compare their priority values. If the priority value of all the three switches are same, then we look at their MAC addresses, and whatever switch will have lowest MAC address, that switch will become my root bridge of the topology. Okay. So by default, the priority of switches is going to be 32,768. The default priority of switches will be 32,768. And this priority can be modified, but only in the multiples of 4096. That means if you wish to change the priority, it has to be in the multiple of 4096. You can either set the priority as 0 or 4096 or 8192, or we can say you can keep on adding 4096. And this goes up to the maximum of 61140. Okay, so it ranges between 0 to 65,536. But as I said, it can only be configured in the multiples of 4096. So the maximum you can set as your priority is 61140. Clear? So if in case the priority value of all the three devices is same, which is the default priority 32768, then in that case, what do we look at? We look at the lowest MAC. Okay. So we will assume that all the three switches are having the default priority and their MAC address is 1111, 2222, and 3333 respectively. So obviously these are some hypothetical assumptions. MAC address don't look like this. They are longer addresses. Here to make things simple and for our understanding, we are using it as 1111, 2222, and so on. Okay. Now, if the priority value is same for all the three devices and we look at lowest MAC address. So what do you think? Which out of the three switches has the lowest MAC address? Who will become root bridge of my topology? Perfect. It's going to be my switch number one. Yes, Syed, if the lowest priority is there, we will look at the priority first to compare and find out uh, who is the root bridge of the topology. But if priority is not there, then we look at MAC addresses. And as per the MAC addresses, switch one has the lowest MAC address, correct? So why in my topology, I can say my switch number one will become the root bridge. Clear? Now, root bridge is nothing but simply the master of the topology. We can say it as the decision maker who will take care of everything else, which we are going to speak about later on in the session. But as of now, are we all clear about how a root bridge is elected? Perfect. After the root bridge election, the next election that takes place is root port election. Root port. So let's first of all define what is a root port. It is the physical interface present on non-root bridge that allows you to reach root bridge with the lowest STP cost. Okay. So we discussed that we have three switches: switch number one, switch number two, and switch number three. And as per the MAC addresses, we have finalized that switch number one of my topology will become the root bridge. So that means switch 2 and switch 3, these are non-root bridge, right? So root port, like we have written here, root port is the interface present on non-root bridge that allows you to reach root bridge with lowest STP cost. Okay. Before we speak about cost, let me tell you the default cost values which we use for different types of interfaces. For Ethernet interfaces, we consider the STP cost as 100. Okay. For fast Ethernet interfaces, we consider the STP cost as 19. For gig Ethernet interfaces, we consider the cost as 4. And for 10 gig, cost of 2. Assume that I'll just make it again a little more neat and clean. Okay, assume that all these devices are connected to each other using fast Ethernet interfaces. So here is 0/1. This is 0/2. Similarly, 0/1, 0/2, 0/1, 0/2. This is my root bridge, first of all. So I'll not have a root port on my root bridge. I will have it only on non-root bridge, which is switch 2 and switch 3, correct? Now we said that these are fast Ethernet interfaces. So that means the cost to move from S2 to S1 would be 19. Similarly, for the interface connecting S2 to S3 would be again 19, and S3 to S1 will also be 19, right? So guys, Now this is my non-root bridge, right? I have two ways to reach root bridge. One way is via 0/1. One way is via 0/2, like this. If I go via 0/1, my cost considered would be 19, correct? But if I go via 0/2, it will be 19 plus 19, 38, right? So as per the define, root port is the one that allows you to reach root bridge with lowest STP cost. So can I say that on S2, 0/1 will become my root port? Yes or no? Why, Sanju? Sanju, you have said no. What do you think? Why? Ah, okay. Similarly, on switch 3, I have two ways to reach root bridge. This is having cost of 19. This will have a cost of 38, right? So on switch 3, let me know which interface will become root port. Perfect. This one will become my root port. Awesome. Okay. Now the last election is designated port election. So guys, a designated port is the port which always stays in the forwarding state. Okay. So very first thing to always remember about designated port is that all interfaces of root bridge are by default going to be designated ports, according to which 0/1 and 0/2 of my switch 1 both will become designated ports. Clear? Okay, we have some questions. Why we gave root port on switch 3? Switch 3 is also a non-root bridge. So that's also going to have a root port. That's for S2. So yeah, like for S2, it's going to be a different port. For S3, it's going to be a different port. But in STP, only one root port is considered. No, Mudassar, that's not correct. That's not a true statement. In STP topology, there can be multiple root ports. Yeah, the root bridge can always be one. Exactly. Nancy has mentioned every bridge, every rather than bridge, I should say every non-root bridge will have one root port. Are we clear, guys? Okay. So like I mentioned, all of my interfaces of root bridge will by default become designated port. So in my topology, S1 was the root bridge, right? So according to which 0/1 and 0/2 of my switch number 1 will automatically become designated port of my topology. Now, guys, if we pay a little attention, we are just left with two interfaces, one 0/2 of S2 and the other 0/2 of S3. Between this segment, one interface will be blocked interface and one will become the designated port. The question is who will become designated and who will become the blocked port. First criteria of finding out the designated port is cost of the switch to reach root bridge. So if you compare the cost here, the cost to reach root bridge from switch 2's 0/2 is 38. From switch 3's 0/2 is also 38. So that's a tie, correct? Now, switch with lower bridge ID will be used as tiebreaker. Here I have a tie of cost, right? So the next thing that we look at after cost, first criteria is cost. Second criteria is switch with lowest bridge ID. So between S2 and S3, which switch has lower bridge ID according to you? Also, why? Yeah, good job, guys. It is switch 2 having the lower bridge ID because it has a lower MAC address. So we can say that switch 2's 0/2 will become designated port and my 0/2 of switch 3 will become the blocked port. This is how my STP will decide which interface becomes the blocked port, which interface becomes the root port, and which one becomes the forwarding one. Let me know what question or confusion you have so that I can explain you again. Okay, I'll give you the understanding on designated port election again. So first of all the interfaces of my root bridge will by default become designated ports. Okay, according to which S1's 0/1 and 0/2 will become designated port. Second is finding out the designated port between these two. First, we consider cost. Okay, so comparing the cost of these interfaces between my S2 and S3, we find that the cost is same, right? For both the interfaces that I have here in my topology, the cost that we have is same. So after cost, the tiebreaker is going to be my switch having lower bridge ID. Bridge ID is made up of two things, priority value and MAC address. So the MAC address that we considered for switch 1, switch 2, switch 3 are as follow. Between switch 2 and switch 3, which switch according to you have the lower bridge ID? It is switch 2, right? So simply speaking, switch 2's interface 0/2 will become my designated. According to C, the cost thing is basically finding out lowest path cost to root bridge. So if you compare the cost is going to be same from both the sides, isn't it? So that's a tie. Now the tiebreaker is lower bridge ID. And because switch 2 has got lower bridge ID, the interface will become designated port and the opposite one will become blocked port. Is that clear now? All right. Then let's also speak about some timers which work in spanning tree protocol. No, Ankush. Bridge ID, see, bridge ID is made up of two things, priority value, MAC address. We assumed that priority value of all the three switches are default priority, which is going to be same in this situation. So next thing that we look at to find out who has a lower bridge ID is MAC address. We are assuming MAC of switch 2 as this and switch 3 as this. Who do you think have a lower bridge ID now? Switch 2, correct? 19, which you are talking about, is the cost of the interface, the default cost, which we use for fast Ethernet. That's a different thing. That's not your bridge ID. Clear? All right. Now, the next thing that we are going to talk about is SGP timers. There are some timers which work in spanning tree protocol. Basically, there are three timers. First is your hello time. Guys, I told you after a certain time, BPDU messages are exchanged. Can you recall what was that timer? 2 seconds, right? So the hello time in STP is 2 seconds. Then there is a forward delay time, which is of 15 seconds. I'll let you know what exactly it does. And then there is max age time, which is of 20 seconds. So let's understand something about port states, which will help us in getting a clarity on what is this forward delay time and what is this max age time. Okay. So there are some STP port states which an interface goes through before becoming an active or forwarding interface. Let's understand what are these port states. An interface goes through 5 port states, in which the very first one is disabled. As the name defines, disabled is when your interface is down. When your interface is down, we can say that the state of my interface is disabled. Okay. Second is listening. Third is learning. Fourth is finally forwarding. And fifth is blocking, the interface which is blocked. Okay. So when you turn your interface on, it moves immediately from disabling or disabled to listening state. Now, in listening state, it can participate in BPDU exchange. Okay, so I'll write it down. In listening state, the interface can participate in BPDU exchange. From listening, it moves into learning state after 15 seconds. Okay. After 15 seconds, it gets into the learning state. In the learning state, the interface can exchange BPDU and can also learn MAC address of connected devices. Here. So now it can not just exchange the BPDU messages, but can also learn the MAC address of the devices which are connected. From learning, it moves into forwarding again by taking 15 seconds. And this is basically the timer, guys. These 15 seconds timers is nothing but the forward delay time, which we have learned earlier. So it takes another 15 seconds to get into forwarding. And as you might be able to guess already, now it can exchange BPDU, can learn MAC address, and can also forward traffic, because now it's a forwarding interface. Clear, guys? Now we again have a question, another question. What is then this max age time of 20 seconds? Let's understand. Let's say you have this topology S1 connected to S2 connected to S3, and spanning tree elections has taken place. This interface is blocked. Okay. And assume after some time, this primary link goes down. So this link is now down. So my blocked interface will first of all wait for 20 seconds, which is your max age time. Clear? So it will wait for 20 seconds. After 20 seconds, it will get into listening state and then will basically continue with the same timers to get into the forwarding state. So the max age time is the time a blocked port waits for the interface to come up. And if after that 20 seconds, the interface still doesn't comes up, then my blocked interface is changed into the forwarding state after obviously the forward delay timers. Okay. This is how the whole spanning tree works. Questions or doubts in this? Nicholas, we haven't spoken about RSGP, so let we get there. I'll let you know how the timers change in that situation. BPDUs carries bridge ID, Ankush. So basically, guys, spanning tree has got multiple standards. Okay. The one that we so far have discussed is standard spanning tree. You can say it has got multiple flavors. Okay. The standard one is represented with 802.1D. It is the IEEE standard, which we are using for spanning tree protocol, the standard one. Mudassar, the one that you have mentioned is rapid spanning tree. We will learn about rapid spanning tree now. Rapid spanning tree with the IEEE version 802.1W. Okay. Yes, Sayyid. After 20 seconds, it gets into listening, then into learning, then into forwarding. Okay. Now, rapid spanning tree is there, which is a faster version of spanning tree protocol, an evolution of standard spanning tree protocol. This was released, I believe, in 2001. And rapid spanning tree is, we can say, the one that takes the decisions very quickly and is much faster than the standard spanning tree. So in rapid spanning tree, there are only three port states. Like in standard spanning tree, we discussed disabled, listening, learning, forwarding, blocked, right? In rapid spanning tree, there is only three port states: discarding, learning, and forwarding. Discarding, learning, and then simply forwarding. Here also, the messages are exchanged every 2 seconds, but there is no max age time. Rather, if a switch misses on sharing 3 BPDUs, STP considers it as down. And transitions the blocked interface into forwarding interface. So now things are different. I am a spanning tree switch, and let's say you are also a spanning tree switch. You sent me a hello, I didn't reply. You will send another hello, and let's say I again didn't reply. You sent the third one, and I again didn't reply. So if I do not reply for 3 consecutive BPDU messages, you can consider me as down. You can consider that this switch is no longer available, and you will change your blocked interface into forwarding state. That's how quick it is as compared to standard spanning tree. So the transition and everything takes place very quickly. That's why we call it rapid spanning tree. Okay. So we will have a look on how these configurations look like, or how the details of spanning tree look like, by creating a simple topology of 3 switches in my Cisco packet tracer. So I'm going to take switch 1, switch 2, and switch 3. We'll connect them together like this in my packet tracer. And then we will observe how spanning tree elections are taken place in this particular topology. Then I'll also show you how rapid spanning tree can be enabled, and how fast it becomes comparing it to the classic spanning tree. Shall we proceed? All right, I'll share my Cisco packet tracer window. My window of Cisco packet tracer must be visible. So I will take three switches like we discussed, switch 1, switch 2, switch 3, and I will connect all my devices together. And I want you guys to pay good attention on these link lights. You see, right now they are red, then they turn into amber color. They take some time, right? This is nothing but the forward delay time. They're taking time to get into the forwarding state. Can you see my screen? Everyone, please confirm. Yeah, okay. Try to rejoin if you are not able to see my screen. Okay, now you see all the interfaces turned green, but FA01 of switch 1 is still in amber color. That means this is my blocked interface. Okay, so this interface is the blocked interface. Now what will happen if I delete a primary link? Observe this. If I delete a primary link, FA01 will turn into a forwarding interface. There you go. We can see that FA01, which was earlier a blocked interface, now has turned into a forwarding interface, making sure that my switch 2 doesn't loses any reachability towards switch 0. That's how spanning tree works. If I make it again connected, it will block the interface again. So I'll just skip the time. Now you can see FA01 is the blocked interface again. Let's also check the details on these switches individually to find out who is the root bridge. To check the spanning tree details, you have the command show spanning tree. Enter. When I say show spanning tree, it tells me that, first of all, these are the details of my root bridge. So it tells you that the root bridge or root ID has a priority of 32769. MAC address of the root bridge is this. The cost to reach root bridge is 19. The port to reach root bridge is FA0/2. Hello time is 2 seconds, max age 20, forward delay 15. Then it tells you about the local device, where again you can find the priority. Now you must be wondering that the default priority was 32768. So how come it becomes 32769? So here is the breakdown. Priority is 32768. System ID extension is 1, which is simply the VLAN number. So it's currently for VLAN number 1. That's why it adds the VLAN number 1 to the priority, making it 32769. Okay. So that's my priority. This is my local switch MAC address, then timers. And here I can see my interfaces. FA01, FA02. FA01 is the designated port. FA02 is the root port. The status of both of them is forwarding. Because they are fast Ethernet interfaces, the cost is also 19. Then here I can see the priority and the port number. So when your cost is same, when your bridge ID is also same, the designated port election depends upon port numbers. So it is your port number 1, this is your port number 2. Whatever interface will have lower port number, that will become designated port. So we can say in certain situations, when we are not able to identify who will become the root port or designated port, we make the decision on the basis of lower port number. So that's the detail here. Then we have the type. The type of connectivity is P2P, that refers to point to point. Similarly, if I go to switch 2 and check the details, which is my root bridge, show spanning tree, I can see here are my details of root bridge. And it also tells us that this bridge is the root bridge, right? So the local switch that we are looking into is the root bridge. Therefore, both of the interfaces, FA01, FA02, both are designated ports. Make sense? Then lastly, if I check my details on switch 1, we can see here one of the interfaces root interface and the other is the alternative. Alternative means the blocked port only. So that's what we call as alternative interface or alternate interface. Okay. This is how the spanning tree election has taken place, and this is how it is working in this topology. Let me know questions if there are any questions or doubts in this. Sayed, here also the election is taking place on the basis of lowest MAC address because priority is going to stay the same on all the three switches. Something about VLAN, how is the protocol related with VLANs? For every VLAN, we will have a spanning tree instance, okay? Every VLAN will have a separate spanning tree instance. By default, they work in VLAN number 1. That's why the instance is for VLAN number 1. If let's say there are 10 more VLANs, so there will be 10 more spanning tree instances. That's how the per VLAN spanning tree works or the classic spanning tree works. I did not understand why the cost for all switch ports to reach root bridge for all port is 19. It should be 19 and 38. No, Sayed, see. This is my root bridge of the topology. If I check my cost on switch ones, FA01 have the port cost as 19 and FA02 also has the port cost as 19. It will not calculate FA01's cost and FA02 of switch zero's cost, right? That's something that you have to understand, that if it will go via this way, it will also consider the cost which switch zero takes to reach switch two, right? The port cost is 19 only, but the total cost to go from switch 1 to switch 2 via FA01 calculates up to 38. So that's your understanding that you have to take. Sanju will change the cost. No worries. We'll look at those things also. But are we clear so far about the details that we have looked at in the CLI? Yes, Sayed, the port cost in the CLI will remain same, and you have to calculate the distance cost by adding it up. How does device know the switch one is the blocking point? It happens with the elections, Abhishek. That's the whole thing we have been discussing since beginning, right? First, we'll elect root bridge, then we'll elect root port. All those elections have taken place here. And then eventually they got to know that FA01 must be the blocked port, blocking port. All right, I'll give you some time to experiment and explore this details. Create similar topology of three switches. Try to find answers to your questions by yourself first, and then I am here to help you out with your doubts. Okay. So take your time, experiment with it, and then we shall continue with a little experimentations on this particular topology. Ankush, like I mentioned, layer 3 has the concepts of TTL. So looping doesn't occur there. And if it occurs also, there are mechanisms to stop it. To compare the MAC addresses of devices, you can use the same command, show spanning tree. Here you will find the MAC address of your local device. And then similarly, you can check MAC address of the other devices by looking under the section bridge ID. Okay. And you can compare. Turning back to VLANs, can we distinguish the behavior of different VLANs, or will they all work in the same way but in different instances? Nicholas, they will work in the same way but in different instances. There are options to group them together. That's something we learn in multiple spanning tree, but that's a part of CCNP, not our concern as of now. Okay, 5 more minutes. Try to complete the lab and then we shall move ahead to the next discussion. Flapping is basically a cycle of going up and down. If something is repeatedly getting unstable, it's going down and then coming up, then going down, then coming up. That's called flapping. Now it can happen with interfaces, can happen with MAC address, VLANs, anything. And there can be different causes of it. So can't say anything in particular until and unless we know the situation, right? So it can happen for various reasons. And if it is happening, that means there is some problem that you need to fix. Yeah. So I can give you one example. For MAC address, you can assume that if same MAC address is found on two interfaces and there is some loop, let's say some STP misconfiguration is there. So all of this can lead to problems and instability, right? So in such situation, you might find MAC flapping or VLAN flapping. Yes, Ashish, for one instance, there will only be one root bridge. The version or the flavor of spanning tree which will be used depends upon the switch version. So some versions of switch by default works with the rapid spanning tree. Some work with classic spanning tree. So yeah, that can vary from device to device. If we take four switches, then also the same exact elections will take place according to that scenario, and interfaces will be blocked to avoid loops. Yes, Ankush, even if let's say multiple cables are connected between same devices, then also there is a possibility of loops. So there also you will find spanning tree working and blocking the interfaces, which are like after making all the elections, it will block the certain interfaces to make sure that there is no loops. Okay, now we'll create another scenario which we are going to switch as rapid spanning tree. But before that, let's learn how to change priority. Right now, the root bridge of my topology is switch 2, correct? I will change the priority of my switch 1 to 4096 so that it becomes the lowest priority of my whole spanning tree topology and switch 1 becomes the root bridge of the topology. Let's see how we do that. In the CLI, get into the configuration mode and type down spanning tree VLAN 1 priority 4096. If I put a question mark here, you can see it ranges from 0 to 61440 and can only be configured in the increments of 4096. So if I try, let's say 200, so you see it says bridge priority must be an increment of 4096. Allowed values are these. So instead of 200, we'll go for 4096, which is a allowed value. And once I do that, my switch 1 will become root bridge and elections will take place again. So let's see and wait what happens after it. Ashish, that's what we are doing. We are changing priority and manually making switch 1 a root bridge. Okay, now after few seconds, we can see the elections have taken place again and switch 1 has become my root bridge of the topology. If I go back to switch 1 and I check show spanning tree, I can see the priority first of all got changed to 4097, which means 4096 plus the VLAN number 1. And this bridge is the root bridge. Both the interfaces are now designated ports and the blocked one is FA02 of switch 0. Clear? This is the command to change priority. Okay, give it a quick try. Change priority of one of your switch and see how spanning tree elections happen or change the decisions after you modify the priority of a switch. Switch having lowest bridge ID, that means the lowest priority will become the root bridge, not the highest. Sort of 4097 because like I have mentioned earlier also, it's adding the VLAN number to the priority. Okay, I hope everyone must have tried this by now. And if there is any questions, any doubts, any queries again, then you can let me know. Otherwise, we'll move to the next concept where we are going to learn about uh, the concepts of ether channel. So are we good to proceed ahead? Give me a thumbs up. How to change the cost? Sanju, we really don't do SGP tuning in CCNA or SGP manipulation in CCNA. So I'm refraining from getting into a scenario or a situation where our beginners might have to face challenge in understanding the concept. Okay, so we'll keep it simple. We'll not get into we can say anything that's not in CCNA so that we can cater the complete audience, right? VLANs are considered for all versions of spanning tree. Yes, Nancy, the standard, we can say the default spanning tree flavor that we use is per VLAN spanning tree. Okay, so it means for every VLAN, there will be a spanning tree instance. And I see your question, which you have pasted earlier. MSTP is the one where you can group multiple VLANs in one single instance. So for example, for 10 VLANs, I can use a single STP instance. That's multiple spanning tree protocol. Okay. Again, that's not in CCNA, so something we'll not be discussing here. All right. With that, I'm hoping that we all are good with the concepts of spanning tree protocol. Let's quickly move towards understanding how Ether channels work. Okay. Ether channels are used for bundling the interfaces together. Now you see, I have a switch and the switch 3 connects with switch 4. So by default, if you see, it's a fast Ethernet interface. So I can say the bandwidth, the effective bandwidth of this link is what? 100 Mbps, correct? But let's assume that the PCs which are connected to it are sending data of, let's say, 200 Mbps. Now, to forward the traffic at the same speed on the connecting link, either I have to upgrade my interface or I have to change the switch. So after 100 Mbps, the next better link than this would be 1000 Mbps, right? A gigabit Ethernet link, but that's going to cost me a lot, right? So what else we can do is we can add another link here. After adding another link, if you see the details, spanning tree is blocking one interface and the other is active. So basically, even after I add another link between my switch 1 and switch 2, it's still not helping because spanning tree is blocking one of the link to avoid the loops, right? So Ether channel give us the ability to bundle these links together. Ether channel gives us the ability to bundle them up together so that both the links can be combined into one and their effective bandwidth can be increased from 100 Mbps to 200 Mbps. Does that make sense? So Ether channel is something that we will configure in two possible manners. Ether channel can be created using a method called on, which is static method, or using the protocol PAGP or LACP, which are the dynamic methods. Okay. When I speak about PAGP, PAGP is a Cisco proprietary protocol and stands for Port Aggregation Protocol. LACP, on the other hand, is an open standard protocol and stands for Link Aggregation Control Protocol. These are the dynamic protocols that can be used for creating Ether channel, or otherwise the static method is there, which is on. Now PAGP offers two states of interfaces. One is active and one is passive. Sorry, not active, passive, rather desirable and auto. A desirable interface will actively try to perform Ether channel negotiation, whereas an auto interface will passively wait for Ether channel negotiation to get initiated. What does that mean? Let's understand. First of all, there is a static method which is on. So according to static method, let's try to convert this link into an Ether channel. So I will enable the port labels to check the name of the interfaces. So these interfaces are FA0/1 and FA0/ I believe 3. Yeah, FA01 and FA03 are the interfaces that we are using for connecting switch 3 and switch 4. How do we configure them into Ether channel? Let's see. First, I'll go to my switch 3. I will say enable config T, select the range, interface range FA0/1, FA0/3, and say channel-group 1 mode on. So I created a port channel number 1 using the on method, which is basically the static method. On means I am willing to put FA01 and FA03 in a bundle, which will be termed as port channel 1 using the static method. Similarly, on the switch, on the other side also, I have to use the same commands. So I'll go to in this, I'll get in the CLI config T interface range FA0/1, FA0/3, 0/1, 0/3, and then I'll say channel-group 1 mode on. Once I have configured it, you can see my interfaces are restarting. Once they restart, we'll see a creation of Ether channel between switch 3 and switch 4. Let's wait. There you go. Now you see both the links are in up state and are active. Why? Because I bundled them up together. So spanning tree thinks that there is only one link between switch 3 and switch 4. That's why the connectivity is up. And also my effective bandwidth got increased. It's got 200 as there are two interfaces who are ready to forward traffic, each having a bandwidth of 100 Mbps. Make sense, guys? So that's how Ether channel is created. FA01, FA03, then I selected them and configured them into port channel number 1 with the mode as on. Then you can also check the details of the ether channel that you have created by using the command show ether channel summary. Here you can see we have a port channel number 1 having FA01 and FA03. But will it not create loops? No, it will not create any loops because switch 3 and switch 4 think that there is only one link between both the switches or both the devices. They logically think that there is only one interface. It is us who know that it is two physical interfaces which we are bundling up together. Okay. Now the question is that how does PACP uses this? PACP uses this with two different states, desirable and auto. Okay, I'll take two more switches and this time we will use PACP to create ether channel. But there is some details about PACP before we jump onto the configuration. Desirable says that it will actively try to create ether channel, whereas auto says it will wait for ether channel negotiation to get initiated. What does that mean? That means that if one of my switch is desirable and the other is auto, so the desirable one will try to create a negotiation by sending some PACP messages from here to the other side. And the auto switch will just keep on waiting for switch 5 to initiate. So if I have desirable on one side, auto on the other side, do you think I'll have a negotiation? Yes, we'll have a negotiation. Why? Because this one will try and the other one will accept. Correct? But guys, let me know if let's say there is auto on one side and auto on the other side. Do you think there will be a negotiation? No, right? Why? Because both the devices will keep on waiting for each other. No one will initiate the process. So if auto and auto is configured, the negotiation won't happen. So no negotiation. Okay. If I configure desirable on the first side and desirable only on the other side also. Now what do you think? Will negotiation happen? Yes, negotiation will happen because both the sides are ready and trying to create ether channel. So ether channel connectivity would be established. Clear, guys? So let's try to configure switch 5 and switch 6 into an ether channel using the PACP protocol. I'll go to switch 5 CLI. I'll select the interfaces FA01 and FA02, FA01 to 2, and I'll say channel hyphen group 1 mode desirable, enter. Similarly, on the other side, CLI enable config T interface range FA01 to 2, channel hyphen group 1 mode auto. We can skip the time so that we don't have to wait. After we skip the time, we can see the links are up and I can check the details by using the command show ether channel summary. And there I can see a port channel 1 is created using the protocol PACP having FA01 and FA02. Any questions or doubts in this? Don't worry about the commands. I'll share the guide for that. Let me know. Is there any question in understanding the concepts? Okay, don't worry about the commands, guys. I'll take care of that. Lastly, we have LACP, which is the open standard protocol for the same Ether channel creation. LACP also offers two port states with a just different name, active and passive. That's it. Rest everything stays the same. So if two switches are there which you are trying to connect with LACP or which you are trying to put into Ether channel using LACP, you just have to make sure that if on one side you are using active and on the other side if you are using passive, what do you think? Will it create Ether channel? Yes? Perfect. And if we have active on one side and active on the other side also, will it create Ether channel? Yes? Perfect. If I have passive on one side, passive on the other side, will it create Ether channel? No, it will not. Okay. So let's configure switch with LACP now. Enable config T interface range FA0/122 channel hyphen group 1 mode active, and on the other side I'll put it into passive. CLI enable config T interface range FA0/122 channel hyphen group 1 mode passive. I'll skip the time and my configurations are up. And if I check show Ether channel summary, so I can see Ether channel is created using the protocol LACP, FA01, FA02 are participating interfaces. That's basically what Ether channel is all about. Exactly, say the commands are pretty basic and simple. I'm sharing the details on that as well in the Telegram group so that you guys can take reference from it. And then you can take 10 minutes quickly to try the same. Then I'll see if we get time. I'll introduce you to another amazing protocol from the security fundamentals. So try this quickly and then let me know once you are done. A maximum of 8 ports can be actively participating in the port channel. Yes, very well mentioned, Ashraf. Like the number eight plays an important role in the world of networking. But yeah, here it is not related to anything with 2 raised to the power 8 or something. That's just a number that we decided for the hardwares to support in one single Ether channel. So it depends on the hardware capability, not something related to this uh, bits or the octet values. Yeah. All right, guys, I think we are good for the day then. If you are done with this lab, then we will continue in the session tomorrow, where we are going to learn about some security concepts and some more amazing protocols, which will help us in understanding how to block some IPs and perform better implementation of security. So that was all for today. I hope you enjoyed the class. I'll share the notes. Also, I'm sharing the screenshot of this one. So thank you so much. I'll see you all tomorrow at the same time.